Okay, so let's talk about the second semester. For UCCP friends, you guys, technically this is like a brand new course for you because it's separated by 2 semesters. It's kind of like the way pre-calc was last year. It's technically the same class, just split into 2 semesters. It's called Calc Mod A and then Calc Mod B. Basically, it's an entire Calc 1 course. Now, and it's just like if you were taking Calc 1 on campus, this would be like the middle of the semester. Okay? Like this would be if we started the year in the fall, we're like right around Halloween time, you know. That's where we're at. So they learn this in 1 semester where we get the luxury of having it over the course of the entire year. And this is kind of where calc shifts a little bit, where we were talking a lot more algebraically, and we were talking about, okay, find the derivative of this, find the derivative of this, find the derivative of this, and we learned all these whole bunch of rules in chapter 3. Now is when we start to apply those rules and really truly understand what the derivative actually means in terms of a function, in terms of, okay, what does the derivative actually mean by looking at the graph? I will tell you this. Chapter 4 is all about graphing the derivatives. Okay, chapter 4 is a lot about graphing the derivatives and what are the implications of the derivatives on the graph. Now, let me remind you that we will actually cover 3, and it's kind of like 2.5 chapters this entire semester. And I know that seems like, how is that even possible? But we will only cover chapter 4 and chapter 5 in its entirety. Chapter 6, we honestly only do like 3 sections out of chapter 6. And that will take us until like May, whatever. When is your last day? May 14th, is that what it is? May 13th. May 13th. So from now until May 13th, we really are only going to do like 2 chapters. And I know that seems really crazy. But what does that mean? That actually means that chapters 4 and 5, their chapter tests are going to be a little bit more weighty for you guys. They're going to be a little bit more, they're going to mean a little bit more for you guys, okay? Because we will really only have chapter 4 test, chapter 5 test. And then we do cover a couple sections of chapter 6, so there is another test in there, but it will not be nearly as big as the chapter 4 and chapter 5 test. Our goal is to try to get through chapter 4 within the third 9 weeks, maybe a little bit like week 8 out of the third 9 weeks. And then so we can start to cover a little bit of chapter 5 and then get through chapter 5 and a little bit of what we do in chapter 6 within the fourth 9 weeks. I like to try to end it a little bit early. I like to try to get more done in the front end. So maybe we'll get closer toward the end of chapter 4 in sooner than I'd like to. But the reason being is because then we do end kind of earlier than everybody else too. So I have to get your exam done in that week. So if we do have to push it a little bit. But honestly, it's really not that bad. You will find this, though. In chapter 4 and in chapter 5, the homework assignments are a little bit more lengthy. So if you thought the homework assignments were a little bit longer in the first semester, sorry, they're going to be a little bit longer in the second semester. They're going to be the biggest homework assignments come in chapter 4. So once we get through chapter 4, then it starts to ease up a little bit. But I will tell you that chapter 4 is kind of like the biggest stuff that we have. So what is chapter 4 then? Well, chapter 4 deals a lot with graphing. And what we're going to talk about now are, again, the implications of derivatives. Like, for example, maximum and minimum values. I'll tell you that the first part of chapter 4, the beginning piece of chapter 4, is all about what does it mean to have a maximum and minimum values, and what are the implications and the derivatives of those things. Well, what is a maximum or minimum value then anyway? Well, it's any peak or valley of a graph. I'll talk about the application here in a second. But in very, very general terms, a maximum or minimum value of a function is a peak or valley of a graph. Okay? we could have absolute maximums or minimums, or we could have local maximums or minimums. Our job over the course of the next couple sections are figuring out where those places exist, figuring out if they exist, and then figuring out where they exist. Thinking back to when I taught some of you guys in Algebra 2, and I said, okay, let's find the minimum value, or let's find the maximum value of this polynomial. Because we did that. We were given this, weird, funky graph on our calculators, whatever, and we said, okay, I want to find this point, right? So you went to your calculators, you said, okay, find maximum, left bound, right bound, guess, enter, and then the calculator spit out a point to you. What we're going to be doing is finding that algebraically. Because, in all honesty, it's a lot easier than you guys think. But you have to use a derivative to find it. Okay? So, let's talk about the applications here. Some of the most important applications of differential calculus are what are called optimization problems. Now, if you've got friends in AP Calc, they've already done this stuff. Okay? They've already done optimization. They've already done finding the maximum and minimum values of the functions. They have to move a little bit quicker through these things because they have to be ready for their AP test, which is a little bit before the end of the year. Are optimization problems in which we are required to find the optimal or best way of doing something. Some examples include finding the shape of a can that minimizes manufacturing costs. We will do problems like this. We will find, how do we minimize costs? How do we maximize area? How do we minimize certain things? And we do that by using the derivatives. We could think about it this way. If you're thinking about a can, what's going to minimize the cost of the can? Minimizing the surface area, right? Minimizing the actual material that we need to use. So if we want to minimize surface area, maybe we could find the derivative of the surface area formula, and that might help us along. What is the maximum acceleration of a space shuttle? This is an important question when the astronauts who have to withstand the effects of acceleration. What is the radius of the contracted windpipe that expels air most rapidly during a cough? What angle should a blood vessel branch so that as to maximize energy expended in the heart pumping blood? All these things you can use derivatives to help you find the maximum or minimum values of those functions. Okay. Now, let's talk about maximums and minimums. Before we get into the application, we have to understand what are maximum and minimum values. Well, by definition, we can say that the absolute maximum value of a function f in a certain domain, is f of c is greater than all other f of x's for every x value in the domain. What does that definition mean? That means that at some point c, the y value at that point c is bigger than all other y values for every other x within that domain. For the absolute minimum, you would say, well, if you got this function f within its domain D, then that point C, if you find the y value at C, if you find f of C, it's less than or equal to f of x, where all other x is within that domain. Okay, this is absolute maximum or minimum values. You might see the book read, or if you're looking things up online, you might see global, that term global maximum or global minimum. That's another way to say absolute maximum or absolute minimum. Okay? Like, for example, here. You see this point right here, that 3, 5. We would say that the maximum value of that function, the absolute maximum value of that function is 5. We know it exists at 0.3, 5, but you would say the absolute maximum value of that function would happen at 3, which is 5. See, we have to make a distinction between where it happens and what it is. The y value is the maximum or minimum value of the function. The x value is just the location at where it occurs. So you would say that the absolute value, absolute maximum would be 5. The absolute minimum value of this function 6 comma 2. It happens at 6, but it is 2. The y value is 2. So that's the way to speak about it. That's the way to talk about it. The value is the y value of the function. The absolute or absolute maximum or absolute minimum are the y values of the function. Okay. Now, we can also have these things because there are always, I should say always, but there are often little peaks and valleys within any function, right? So how do we talk about those? Well, we talk about those in terms of local minimum or maximum values of the function. Now, how does that change the definition? Look at local maximum. It used to say every value where C is that's bigger than anywhere X is for all values within the domain. Then we're going to change that here to say only near that value. Okay? So the definition of a local maximum is saying the local maximum value of f if f of c, so some point c within that function, where it's bigger than any other f of x, but only when x is near that value c. Both left side and right side, and that's an important distinction as well. Local minimum value, same thing, but the y values just have to come smaller than any x value, any other y values around c. Okay, that is what it means to be a local maximum or local minimum. Like here, this would be a local maximum. This would be another local maximum. This would be a local minimum. This would be another local minimum. And then it looks like, would I call this one the absolute minimum? No, because look down here, right? That is not the absolute lowest point of the function. Would I call this one the absolute maximum? Yes, because it never goes beyond that point up top there. Okay, so we have to kind of clarify what are absolutes, what are locals, and so on. Okay, a couple points here to bring up is that if I say this was a closed interval here, look at the absolute maximum of this function. I hope we would all see that this is the absolute maximum of that function. Would you guys all agree with that? That is the highest point on that graph. That is not a local maximum. Okay? You cannot call that a local maximum of the function. And why not? Because you don't know what's happening on the left side of that function. Right? Near C includes both left and right side of C. You only know that it's just going to stop at that value. So where it is not a local maximum, it is an absolute maximum. Okay? You have to make that distinction. An endpoint can never be a local or local minimum or maximum. Okay, let me repeat that. An endpoint where you end it in a closed domain, an endpoint cannot be a local maximum or minimum. Okay? And actually, let me go so far as to say this. I might be getting ahead of myself just a little bit, but if I had put an open dot on that, is there an absolute maximum anymore? No, there is not. Because where it is going to get close and close and close to, what would that be, 8? Right? It would look like it would be getting closer and closer and closer to 8. Does it ever reach 8? No. So what are you going to say, 7.9? No, because 7.99 is there. So you're going to say 7.99? No, because 7.999 is there. And it will get infinitely close to 8. You could say the limit will go to 8, but you cannot say the absolute maximum is 8. That's not how you say that. Okay. All right. Consider this function. The problem for this in the book, I had to hide. Like it's right here. I got a white box around it. But for right now, we're just going to say, consider this function, f of x is equal to cosine x. What we're going to look at is all of the local and absolute maximum or minimum values of this function. Okay. Just based on our knowledge of cosine. Now, think about what cosine looks like. I'll give you a little hint. It's right here. Think about what cosine looks like. Right? It's got a peak at the starting value at the axis. It bottoms out at pi. It peaks again at 2 pi. it will bottom back out at 3 pi. And that process will continue forever. Right? That process will continue forever without restriction, as long as I don't restrict any of my domain. Ooh, come on, I wanted a pen, please. There we go. Right? That will continue on. We should put arrows, right? So if I wanted to define what the local and absolute maximum and minimum values are, here's how we would write it. We would say the local and again. The local and absolute maximum. Now, how do I know that it's going to be absolute? Well, is it ever is cosine ever going to change on the left and right side of this? No, it's just going to keep cycling back through over and over and over and over again, right? If I draw a horizontal line here, it's never going to be higher. Oh, that's pretty good. It's never going to get higher than that point, than those points, right? So we can say the local and absolute maximum values are always all going to exist at those places. Now, what are those places? Well, we would say 0, 2 pi, 4 pi, 6 pi. We can say 2 pi n, where n is any integer. Where n is an integer. That's an n element of z. All the local and absolute maximum values are 2 pi n, where n is any integer. Okay, then we can say the local and absolute minimum values. So where's it going to bottom out? Well, it's going to bottom out at pi, 3 pi, 5 pi, 7 pi, all the odd values, right? And even at -1 pi, -3 pi, -5 pi, and so on. So we're going to say pi plus 2 pi n in all rotations of that, as long as n is an integer. Okay? So it's all rotations because, again, all those terminal angles are going to have the same, are all going to have the same y values. Try to see if there's anything else I need to say about that. Yep. Okay. So let's see, what about x squared? What about x squared? We're going to find any local or absolute minimums or maximums. We're just going to kind of look at it, investigate it a little bit. What about y equals x squared? F of x is equal to x squared. Okay, I see a bottoming out point. Is that a local, absolute, or both? Both, right? It's both a local and an absolute. Minimum value. It's the local minimum value. Now, hold on a sec. I think I have to go back to my last problem. I'm going to finish out this one, and then I think I want to clarify what I said on the last problem. The local and absolute minimum value. Where does it occur? At 0. What is the y value? 0. So the local and absolute minimum values, and I'm going to write this, equal 0. And where do they occur? They occur at 0. I say plural. It's not plural. Just one. The local and absolute minimum values are 0. Is 0, and it occurs at 0. Let me ask you: are there any maximum values? Are there any maximum values?
No.
No, because it will go on forever. X squared will go on forever on the left and the right side. So we will say no local or absolute maximums. Let me go back and clarify something about my cosine problem. Because you know what I defined here? I defined where they are happening, right? I defined where they are happening. I said this is happening, and I need to clarify this, at 2 pi n. And I said this is happening at pi plus 2 pi n. Okay? I say that's where those things are happening. But what is the absolute maximum value of that function? What is the y value at 2 pi n? 0, 4 pi, 6 pi, 8 pi, 1, right? And it's actually equal to 1, right? The actual maximum value is 1. What's the actual minimum value? -1. See, and we should state those things. We should be a little bit more specific when we write them. We should really define where it's not only where it's happening, but what it is. Okay? Give both x and y coordinate of where it's happening. Okay. Let's take a look at x to the third. Just giving you more examples of what does it look like for maximums and minimums. What would you say about x to the third? What would you say about x to the third? Are there any maximums or minimum values?
No.
No. There are none. There are no absolute or local maximums or minimums. The only weird part that's happening here is 0, 0, right? So maybe there's something happening at 0, 0. Maybe it's a local maximum or local minimum. Well, think about this. Our definition of a local maximum or minimum was, take maximum, for example. A local maximum happens when the value of the function is greatest around that point. Okay, so the y value is 0. Oh, all these are lower than it. Good. But are these? No. Okay, so near 0, the y value is not the biggest, so it's not a local maximum. Minimum's the same way, except it's not the smallest point around that value. So therefore, it's not a local maximum, not a local minimum, definitely not an absolute maximum or absolute minimum, because it's going to go on forever left and right. So we would say there are no maximum or minimum values. So let's get a really weird, wacky function going on here. I give you the graph here. This is the graph of the function 3x to the 4th minus 16x to the 3rd plus 18x squared along the domain -1 to 4. Ooh, so it's a closed interval. This is a closed domain from -1 to +4. And it's showing all the values in between. We're going from -1 comma 37. Looks like it's bottoming out at 0, 0. Topping out at 1 comma 5. Bottoming out again at 3 comma -27. And then our endpoint looks to be up here at 4 comma. Why did they give us that point? I don't know why. Let's run it real quick. Come on. Come on. Let's run that point real quick. 3 times, what's that, 4? Yeah, 4 cubed. Oh, no, to the 4th, excuse me. Minus 16 times 4 to the 3rd plus 18 times 4 squared. 3 times 4 to the 4th minus 16 times 4 to the 3rd plus 1, 18, 4 squared. 32. 4 comma 32. Okay, let's identify all local and absolute maximums or minimums. Okay, so let's start local minimum. Okay, the local minimums. Where are the local minimums? At what x value do they occur? And I say that plural on purpose. Where do they occur? Where are the bottoming out points? 0 and 3. Local minimums at 0 and 3. And what are they? Well, they are local minimums equal 0 and negative 27. Okay. They occur at 0 and 3, and they are 0 and negative 27. Those are the bottoming out points. Let's identify local max. Where's the local maximum at? Just 1. Are the endpoints local maximums? No. They can be absolute, but they cannot be local. Okay. So we say just at 1, and we can just put in equals 5. Okay, let's talk about the absolute minimum. The absolute minimum. Where does that occur? Where's the absolute minimum? At 3. And what does it equal? Negative 27. The absolute minimum occurs at 3, and it is negative 27. And then we can say the absolute maximum. Absolute maximum. Well, where does that occur? Where is the absolute maximum? At negative 1, right? This is the highest point of the graph, right? At negative 1. It happens at negative 1, and it is 37. So, this is just a reminder that the absolute does not have to be a local, right? Can it be a local? Yeah, and that's what we see here with the local minimum and the absolute minimum, right? The local minimum, the absolute minimum is a local minimum, but the absolute maximum is not a local maximum. It doesn't have to be. And the reason that it's happening that way is because this is a closed interval, right? Because this is a closed interval. Okay, so now we have what's called the extreme value theorem. The extreme value theorem. Because honestly, when we talk about the local maximums and minimums and absolute maximums and minimums, what we're talking about, we can characterize that as the extreme values of the function. The extreme value theorem says that if f is continuous, and that's a really important piece here. We studied continuity in great depth. As long as the function is continuous, if f is continuous on a closed interval, okay, that's another key piece here. This is kind of like the if statement. As long as f is continuous and closed, then f attains an absolute maximum value and an absolute minimum value at some places in between those closed intervals. Okay? This is kind of an illustration here for you. If you've got closed intervals a to b, however it varies in between there, okay, there must occur an absolute maximum and an absolute minimum within that. Okay. The extreme value theorem is illustrated in this figure down below. Note that an extreme value can be taken on more than one place, right? Like, for example, that last illustration there. I have 2 different places where there's an extreme value. Obviously, one's got to be bigger than they don't have to be bigger than the other. They could be the same, but then they would end up being the exact same absolute maximum. Okay? You can have them the same, you can have them different, and one that would be bigger than the other then, obviously. So there must be absolute maximums or absolute minimums, and local maximums and minimums in that case as well. Okay? There's only one instance where you would not have any absolutes, or not have any locals, but you would have absolutes. And it would look like this. If you've got, so here's A and here's B. If it looked like that, would you have any local maximums or minimums? No. But would you still have absolutes? Yeah. And actually, in this case, the absolute maximum is the same as the absolute minimum. Right? It's both that same value, whatever it may be here. Like, we used all letters. E. Whatever. Maybe 2.718287. Okay. Questions about that? Okay. What's my next example here? This is just to. It's important to note that if the if statement doesn't apply, you can't use the then statement. Like for example here, can we use the extreme value theorem on these cases? The answer to that is no. You cannot. The reason being is because, well, in the first option, in figure 9, that's not continuous, right? There is a discontinuity there. There's a jump discontinuity. So therefore, if you have a discontinuity within your closed interval, even though I do have a closed interval, I've got closed dots on either side. If you have a discontinuity within the closed interval, then that extreme value theorem does not exist. It doesn't have to be an absolute maximum or minimum within that range. Because, for example, here, would we consider this an absolute maximum? No, we cannot consider that an absolute maximum. Okay, we cannot, because what are you going to say? This looks like it's like at 1,3, right? It looks like it's happening at 1. But what is the maximum value then? 2.9, 2.99, 2.999? It's leading to 3. The limit is going to 3, but it's not reaching 3. The actual maximum value of that function is not 3. It's not reaching 3. Okay? Take, for example, this one. The reason we cannot use the extreme value theorem here is because this is not on a closed interval. Okay, we cannot use that because it's not on a closed interval. Like, for example, what is the absolute maximum value of that function? It doesn't exist because it's going to keep going on forever and ever here. It's going to keep going on up and up and up with this vertical asymptote on the right side. What is the absolute minimum value of that function? Well, it's got an open circle on the left side of this thing. So what are you going to say it's at? 1.1? 1.001? 1.0001? You can't tell because it's going to lead toward 1, but it's never actually going to get to 1. So you have to have the if statement for the extreme value theorem to produce the then statement. It's got to be continuous and closed to say that there must exist an absolute maximum or minimum value within that function. Okay. Last thing here, and I'll close on this, and this is where we'll pick up tomorrow. This is a huge statement that we will have here. This guy Fermat, pretty famous mathematician, Fermat. First name's Pierre. Pierre Fermat. This is his theorem. If f has a local maximum or minimum value at c, this is a big statement. If f has a local maximum or minimum value at c, and if f prime, what is f prime? The derivative. If f has a local maximum or local minimum value at c, and if f prime exists, if the derivative actually exists. Okay, when does it not exist? At discontinuities, at corner points, right? All those the kinks in the graph. If f has a local maximum or minimum value at c, and if f prime exists, if the derivative actually exists, then where does c occur? When the derivative is equal to 0. That's an extremely powerful statement right there. Okay? One that we probably could have gotten to on our own, but that's a very, very powerful statement. let me show you a continuous graph that is always differentiable. Okay, maybe some weird one that looks something like this. Take a look at where all the local minimum and maximum points are. Okay, there's one over here, there, here, there, here, there. And it looks like it might bottom out again, but we don't know that for sure. Now, take a look at what the slope of the tangent line would be at all of those points. What's happening at all of those peaks and valleys? The tangent line ends up having it ends up being horizontal. What's the slope of any horizontal line? 0. So what this theorem is saying is that if there is a local maximum or minimum value that occurs, now the hard part about this is that is figuring out which one. Is it a local maximum or is it a local minimum? If a local maximum or minimum occurs and the derivative exists at that point, then the local maximum or minimum must occur when the derivative equals 0. So if you can find the derivative and then set it equal to 0, you can tell where that location is. And that's really honestly what the calculator is doing when we did it back in Algebra 2. The calculator was finding the derivative, setting it equal to 0, and solving that equation. Just really quickly. Uh-oh. Mr. Parker's calling. Hello? Hey. Anyway. Yes. Mm-hmm. Yeah, you got to make sure that the date is on that December, whatever it is, Thursday. I can't remember. Lee sent an email with the exact date that you had to put it on. I don't remember it offhand. I can't remember it. I'm not sure. I think it's probably the Thursday. Was that the 16th? Then I bet that's what it is. Yep, no problem. I'm the resident Kansas guy, other than Mr. Palama. Okay, so this is where we'll pick up tomorrow. And this is a very powerful statement. This is actually a statement that we will use like all of chapter 4. The fact that the derivative equaling 0 is going to be our local maximum and minimum points. Okay. All right, let me stop my video.